My name is Borodovsky. For the last 25 plus years, I work at Intel. I work in lithography probably for closer to 30 years now. In terms of challenges of lithography, I think you can see a distinct three phases that I could see. One was a phase when we can run at Rayleigh coefficient factor was 0.5 or larger. And this was at the time when our vendors were able to change wavelengths and raise numerical aperture pretty much in accordance with the cadence of Moore's law. So we would get most of the resolution benefits just from a stepper or whatever was an imaging tool at the time, with relatively minor advances in mask making and resist formulations. Then this march kind of slowed down. And so we have to invent a lot of techniques to continue marching on Moore's law when numerical aperture and wavelengths combined would not really provide enough resolution enhancement every 2 years. And so this when a lot of resolution enhancement techniques came about. And it was a terrific decade to be a lithographer because innovations were coming right and left every day. And it was a joy to learn all of those things and be part of it. And optical proximity, which was a big part of resolution enhancement, was a significant part of doing that. And adjacent technologies like chemically mechanical polishing was another enabling technique that allow us to go toward very low K1. And we were able to push K1 down to about 0.3, 0.28 in production environments, which is very close to the theoretical limit of 0.25. And then something else needs to be invented. And pitch division came to the rescue, and so people now, and Intel as well, continue march in terms of Moore's law using pitch division and everything else we learned before. There are numerous NGL in the horizons, and NGL stands for next generation lithography. And unfortunately, it's always next generation. I really want one of them to be this generation lithography. So hopefully somebody will coin the phrase, which will be TGL, not NGL. I'm really interested to know which one it is. Everyone knows about extreme ultraviolet technologies, which is technology in development probably for a good 20 years now. Most of infrastructure is developed by now. I think industry really waits for a source power to reach its intended value, for pellicle to show up, and for mask making equipment to complete infrastructure development for EUV masks. I think people underestimate the importance of development of OPC for EUV. Most of the people assume EUV will use EUV mask, and in their mind, the EUV mask is a binary mask, which is not. It's a very complex phase-shifted mask, and making optical proximity correction on those masks will be quite a challenge. Another is massively parallel electron beam. This technology is also very old, also under development for a long time. And another one is directed self-assembly, which is long technology in terms of academy development. I think also for the last 20 years, academy understood what directed self-assembly is. And now for the last 3-4 years, it's a very prolific field for people who start looking into technology to see if it can be taken from lab to the fab, so to speak. I think each one of them has their own chance. What I mean, extreme UV lithography benefit from consensus of industry for many years that that's a technology that will become TGL from NGL. So massive amount of money and resources went into it. There is a vendor who committed to deliver this technology. It's a lithography vendor. There is, as I said, the whole infrastructure around it being developed. And everybody really would love to see this happen. But it's late. Late in terms, late against what we expected it to have. So we have to continue to extend current technology, which is getting more and more interesting. In terms of EB direct write, there was tremendous progress over the last 2 years. Yesterday presentation from IMS actually demonstrated uniformity numbers for patterning with this tool, which are just out of this world. Fantastic. I mean, everybody in the room who saw presentation of Christoph Klein, I think, were blown away. DSA is a remarkable technology that seems to be allows people at relatively low cost, or cost which is much smaller than anything else, to produce fantastically complex pattern at very, very low pitch, which is currently at the cusp of what either EUV or a bidirect write can do, but it has their own issues, not probably the right word. There are all complexities that people are yet to understand how to deal with in order to bring it to manufacturing. So each of them has their own barrier to jump over. I think EUV has one last high barrier, which is a power. bidirect write is have a couple of barriers, and one of them integration with tooling required for fabs. And DSA is yet to jump over many first barriers, which normally any new technology face when it goes from university to the fab environment. Well, I don't think anybody question if we're going to reach the next node. Everybody marching to the next node and node after next and node after next. That's not the question. Question is what's the most economical way of making high volume manufacturing for next node. And this, I think, is subject of debate and bifurcation in the industry, meaning a company like Intel, which is integrated device manufacturer, might execute next node in one particular way, and foundries who have to be place who satisfied many customers might pick another one. And memory people who have somewhat different redundancy of their chips and a different business and a different margins and so on, might pick yet another one. So it's never one solution, it's always more than one. It might confuse people who are in the business of writing about these technologies, but normally people who are part of the technology are not confused which road they pick.